So we're looking at two categories: fluid mechanics, fluid statics, and fluid dynamics. So fluid statics connects with fluids that are not moving, and looking at how pressure is transmitted, and that was a bit in the reading. So pressure can be amplified or reduced by means of fluid statics. In a practical sense, it's a great way to move energy from point A to point B over long distances. So you can do that with electricity, pneumatics, or hydraulics. Those are common means to move power over long distances. Over shorter distances, you have drive shafts, chains, belts, that sort of thing. And close distances, you have gears and pulleys and that sort of thing. So we're most familiar with hydraulic and pneumatic systems, and they're really important for a lot of practical use. So both of these can provide very high torque, which is a lot of power, not power, but energy at very low speed. So moving things slowly. So you remember, power is how quickly you apply torque. And those are a couple examples. So connected with hydraulics and pneumatics. I really want to look more at fluid dynamics. That's of more interest to you generally. And this relates to heat transfer. It relates to reducing drag and controlling how fluids behave. So this is important for all of you. So you think if you want to design cars, it's really, really, really important. Well, yeah, it is, but it's also important for other things too. It's important for consumer electronics. It's important for anything that has a velocity. It's important for everything from designing a hand washing station to designing a Lamborghini. So a lot of wide-ranging things that will come into play here. So what we're looking at today is just some foundational elements, and we'll start with drag reduction, which is sort of the thing that you're probably most interested in, that's most evident to you. And then there's some terms. So here we're talking about fluids. So we're talking about liquids and gases, things that have a viscosity that's less than infinity. In other words, if a force is applied to them, the molecules slide. So we'll look more at definitions later, but I didn't want to get bogged down in that right now. There's a worksheet with a lot of terms on there that we'll go over. So there's some really interesting terms associated with fluid dynamics that are just part of the language. So we'll look at three types of drag: friction, pressure, and wave-making drag. And these are important. These three really encompass everything you're concerned with largely. Wave-making drag is, I'm going to start with because it's the least important, and it's an issue for open channel flow where you're lifting a fluid up against gravity, like this bow wave on this tanker here. So there's a bulbous bow underneath this that sticks out and is pushing the wave up to counteract the trough produced by the hull itself. But by lifting up this water, you're creating drag, and that makes sense. Lifting up something against gravity is using energy. So that's wave-making drag. It's an issue, again, with what's called open channel flow, like drains and streams and things like that. So I have to say it's probably not really applicable to what we do, but I just want to put that as a category of things. And then friction and pressure are the other two categories. And here's another image of wave-making drag. So you can see a stream. This is a nearby stream. You see a trough behind a pillar and how the water piles up on top of the trees, these flooded trees. So that's using energy, so that makes sense. It's a type of drag. So if you're trying to reduce drag, you want to reduce that wave-making density. And this is friction drag. So it's kind of a scary graph to get started with, but we'll look at friction and pressure drag. Friction drag is the easiest one to understand. It's resistance to flow based on surface finish. So I'm just going to look at this for a moment. This is on the left here, you see friction factor. On the right, Reynolds number, which is basically velocity. We'll look at that more later. But what this is saying is that when that things that have higher friction going up on the scale, they have more drag. Okay, that's what that means. Rougher things have more drag than smoother things. So here, this has to be for piping. Smooth pipe down here, rougher pipe up here. So roughness normally gives you more friction drag. And you'll notice some other terms here connected with turbulence and laminar flow, which we'll look at later too. It has to do with boundary layer, which is an important issue. So that's kind of straightforward, I think, in terms of friction drag, because you're used to that in your everyday life. Like sandpaper has more friction than leather. So this is looking at pressure drag, and this is a function of geometry. So when you hear about coefficient of drag and these sorts of things, that's where this comes into play. And this is based on geometry. And what's very interesting for us is we're talking about form again. And so when we spoke with moment of inertia, we talked about form and how we can vary form to achieve results that we want. So we can make things more efficient, almost free. And this diagram shows you, the top diagram shows you we'll say this is water, so it's hydrodynamically efficient, it's streamlined, so that the water hits this boat and it goes around the boat and it recombines behind the boat in sort of a seamless way. The bottom boat is a barge, so the water comes up and smacks it at the bow and then goes around the bow and then creates these eddies behind it. Well, you can intuitively imagine these eddies produce a low pressure, and this impact at the bow produces a high pressure. So this pressure difference between the bow and the stern, if I go right on this or not, the bow and the stern is called pressure drag. So that's the pressure across this bow. So high pressure here where my mouse is, low pressure here. If you look at the streamlined version, it's fairly low pressure here and well, a smidgen higher than the normal pressure because it's so nicely streamlined, a smidgen lower in pressure. So the pressure drag here is much less than the pressure drag below. And we'll look at some other examples here. So these are wind tunnel results. So you can see this aerodynamic foil on the right, that the gas flows around it and recombines. Whereas these other ones, like this truncated one here, you get this low pressure section. So what you have is a vacuum cleaner behind this airfoil in this case. It's trying to suck it backwards. It's trying to suck it the wrong way, which is good if you're trying to draw fuel into something like a carburetor or create a vacuum, but generally it's not good. So here's an image of a vacuum being produced behind this foil. And well, the round one, you see there's actually separation, which we'll look at later. We'll talk about boundary layer, but there's sort of the lower pressure behind the round cross section and the higher pressure up here. And I even have a diagram for you. Let's see if that shows up in the webcam. Okay, so this, you're a designer, this is a shape. This is kind of okay, here's a shape of something, a little submarine, let's say. Well, I can very simply change, so the friction drag is the drag across the top of this. So it's the resistance of the say, water flowing against the top of this. So it's a function of the velocity and the roughness of this device. But the pressure drag on this is high. So if water is coming, if water comes in here, it hits this, bang, high impact, high pressure, and then I get these eddies over here. So I have a low pressure here and a high pressure here. So I have this vacuum cleaner trying to pull it this way, and this impacting water hitting it this way. And what I can do as a designer is simply change the shape like this, and I've reduced the pressure drag. A little bit of the change in friction drag, but the pressure drag difference between this and this is enormous. It's a big number. It's a real big number. So this is a better design than this is normally. And you say, well, there's more surface area, so there's more friction drag, and you're right, but that's usually a small actor. So if you look at this chart on the left, this is showing you some elements of drag. And again, this is on PowerPoint, so you can spend some time looking at it. But what you see here is pressure drag on the bottom. See pressure drag, it goes up, and friction drag goes down, and we're looking at this airfoil section here. So we're looking at the coefficient of drag on the left. And so you can find sort of an optimal point in any shape where the friction drag and the pressure drag combine to create the lowest total drag, which is right where my mouse is. So you can find the optimal point where this additional friction of having more surface is offset by the improvement of flow based on the form. And again, I'll take questions on this later too after break. On the right is an example of wave making drag and its effects. So this is for maritime. So this is showing viscous drag versus wave making drag. So viscous drag is going to be all the friction of the wave making drag. And then here's wave making drag. So at low speeds, all friction is low. It is a function of velocity. But as you can see here, wave-making drag in a boat becomes really big as they go faster. And this is a conventional displacement hull, so you can do some things to make that number lower, but it becomes a real big element for us. So it's always a function of velocity. Right. Now I'm going to look at, well, let me see if I want to say anything else about that. So wave-making drag, we're not too interested in. It's there. It's something you should know, but it's probably not too applicable. This viscous drag, this friction drag plus pressure drag, is very important. Friction, both of these can be reduced. All three of these can be reduced by lowering speed. Friction drag can be reduced by making things smooth. Pressure drag can be reduced by changing the cross-sectional shape or the form of an object. Okay, and that's design. So yeah, you can kind of wax the car and that kind of stuff to reduce friction drag a smidgen, but pressure drag is really what it's all about. And you may even have a sense at this point that there's more to it, because you think about even aerodynamic treatments of cars and boats and other things. You know, why do you have spoilers and such? And here then we have to look at pressure drag, or at boundary layer. But this is kind of the key elements of drag, those three types of drag. And there's, in the book, I have listings of coefficient of drag for different shapes, so you can sort of look those up. And I also have links to some wind tunnel testing in this PowerPoint that you can look at to kind of get a more of a visual sense of how drag is affected by shape. And we'll talk more about that later too. I want to look at viscosity, and you're familiar with viscosity probably. It's resistance to flow. So when you apply a shearing force to molecules, they flow with different propensities. So things that have a high viscosity don't flow well, and things that have a low viscosity flow really well. So here we're looking at different motor oils, just by way of example. Air has a low viscosity, water has sort of the medium viscosity, and oil has a high viscosity. And your wooden desk has an infinite viscosity, sort of. So when you deal with solids, that's kind of one way to think about it. They have an infinite viscosity. It's not really infinite, but it's really high. And interestingly, plastics are called viscoelastic. They will flow when a pressure is applied to them, sort of like a fluid. So again, fluids are, you know, typically liquids and gases, and solids are solids. And when we look at rheology later, we'll look at mixed things like aerosols and slurries, emulsions, those sort of things. Blood is a big one, where you mix solids and liquids together, so things flow like liquids, but they act strange, including your toothpaste. You may have noticed. It doesn't, like, not all things act like water, and that's what we'll look at tomorrow. This is a chart of viscosities for different types of oil, and just put it up here for kicks. So that's actually the temperature got kind of cut off. So temperature there is on the x-axis, but number 2 oil is what you use in your home. Number 6 oil is what you use in ships. It's real heavy crude oil, so viscosity goes up as a log chart. So you can get this data from different sources. So viscosity is usually a function of temperature. And in a type of fluid called non-Newtonian fluids that we'll look at next class, viscosity is also affected by how fast it flows, or the shear rate, or pumping speed. So, and that's kind of funky, and that really gives you deep insights into fluid dynamics. So again, we looked at drag. I hope you found that interesting, because that's something you hear about all the time. But we're going to keep going deeper and deeper and deeper to unpack elements of fluid dynamics that will take you to a really good point in understanding them, I think. So here I wanted to look at fully developed flow. These are 2 fans. So the top one is a centrifugal fan, the bottom is an axial fan. So the bottom is the type of fan you would have as a cooling fan on a computer, for example. And the top one is a blower you would have in a furnace or something like that. And what you're looking at here are streamlines. And it's kind of interesting. If you look at the top, what's happening is when we, the high velocities, you get higher velocities at the discharge of the centrifugal fan. So you see the higher arrows here on the top. And if you remember last time when we looked at something going on, okay. When we looked at computational fluid dynamics last class, some flow visualization stuff, and we looked at the elbow and how fluid hit the elbow and kind of made a high impact area. Well, that's sort of what's happening here. So the air gets slung out of this fan, and it has a real high velocity. Down at the bottom, it actually has a negative velocity. It might even be flowing the wrong way. And as the air flows through this duct, it develops this profile like this. It's called fully developed flow, and it's fastest in the center, slower at the edges. And the reason for this, there's a lot in this image. The reason for this is the molecules are pulling each other along due to surface forces. That's viscosity. So if one molecule is going faster than its neighbor, it's going to drag its neighbor along due to surface forces. It's a viscous issue. That's the heart of how fluids behave. They don't travel alone. They travel with their friends, and they drag them along. And also, you're looking at boundary layer issues, which we'll talk about also, where you get this point where the molecules adsorb, they stick to the surface of what's restraining them. So you get this kind of interesting effect here, which affects heat transfer and other stuff. And it's a real design issue. Now here you have an axial fan, and you have the same sort of thing. The air is blowing from left to right. And behind the fan, there's no positive flow, but you get high flow here. And as it flows through the ductwork or through air, generally, it starts to, the faster molecules drag the slower molecules until you get this fully developed flow. And there's this distance that it takes for that to occur. So if you're interested in the environment and you design something and you don't understand this, you could, by design, have poor convective heat cooling or heating. You could have poor airflow, whatever it is, because you did not understand this design principle. And you can calculate this length too. It's not hard, simple algebra. So this is important. It's important that designers understand this, so they don't put, let's say, a discharge right here, right, the discharge of the fan, like you're designing something, cooling air or whatever it is, or something to run your Legos machine with a low pressure pneumatic system or whatever. And if you put it in certain places, you won't get positive air. You could make things worse. So all you're going to do is burn electricity and not produce results that you want. This is busy. I just put this up here for kicks. This is pressure drag. This, unfortunately, was the highest fidelity image I could find. If you look, these are different types of valves, and they are like this is a long radius valve, and we don't have to go through this, a T and so on. But this is sort of the traditional way of calculating pressure drop. And what all this is saying is on the right here is the size of your pipe, and then you draw a line like this red line between the size of your pipe and the fitting you're using. And this is just a graphic showing you that certain fittings have a lot more loss than other fittings. So this long sweep elbow is at the bottom, and this globe valve is up at the top, because the water has to do all kinds of incantations and permutations to get through it. So this is a way of calculating pressure drop through weird geometry by using this nomograph here. And it works. It's peaceful. I've used them. And it's a good check on the math type of stuff. And it just shows you this is kind of an issue with pressure drag largely. All right, now we're going to look at laminar versus turbulent flow. And so this is an interesting issue. And I'm going to start on this and introduce this. We'll probably go back and look at this again too. And again, after break, we'll see what questions you might have. But this is expanding on what we talked about before with what was called the fully developed flow, where I showed you an image of the fan and how air blew through it. And this is showing you cross sections of piping, the velocity profiles of piping of different types. And you'll see numbers like Reynolds number, which is basically the velocity. It's actually inertial viscosity. We'll look at that later. So you have different types of behavior when you have high flow versus low flow speeds. So high flow speeds will generally become turbulent, and low flow speeds are laminar.